Hello, this is Mr. Huff. Let's talk about total energy. First, let's consider an easy example before we start looking at orbital behaviors. Okay, so if we look at this skater, let me start this playing. They are going up and down this ramp, and you can see that they speed up and they slow down, and they speed up and they slow down. So we see this interaction of kinetic energy and potential energy, but at any point, you can take the sum of these two and get the total energy. It is the same for this. So we have the total energy is equal to the sum of the potential energy plus the kinetic energy, or it's equal to this expression here, the product of the gravitational constant times the mass of the center body times the mass of the orbiting body divided by 2 times the radius. Keep in mind that radius in this case would include the diameter of the larger, or not diameter, the radius of the larger body that the orbiting body circles. So one of the things I talked about in a previous video is that the centripetal force and the gravitational force for an orbiting body are the same value, which means we can rearrange this to solve for mass times velocity squared. So this is equivalent to mass times velocity squared. So if we look at this, we have the potential energy, which we've talked about, and the kinetic energy, which we've talked about. So now we can replace the kinetic energy with this expression. So that would give us the potential energy times, plus 1/2 the mv squared value from kinetic energy. Then we can factor out these two values here, and we end up with -1 plus 1/2 times this. And if you reduce that even further, really that means negative 1/2 or negative whatever this is over 2. So this is the final expression right here. So that's how we get there. I really don't like this slide in the curriculum. It's very hard to follow what's going on. So they kind of talk about this and they talk about this and they throw this in there, but they don't really explain where it comes from. Blah. Okay, I'm through whining. Let's go on. For the calculations I'm going to have you do in Canvas, again, it's kind of awkward to enter very large numbers, so we're going to solve for some mass values. In order to solve for mass, we need to take this and rearrange it to solve for m. So to get m by itself, we have to multiply both sides by this r square or 2r right here. So we do that, and that goes to this expression of this formula: 2 times re equals minus g large M little m. And to get little m by itself, we have to divide both sides by minus gm. So we end up with this expression here, and that is equal to the mass. Keep in mind this radius is the radius of the Earth plus the altitude between them. We normally don't include the radius of the orbiting object because when you compare it to the Earth or whatever it's orbiting, it's usually not significant. So here's a practice problem to look at. We have an altitude of 720,000 meters and a total energy of negative 1.683 times 10 to the 11th joules. It's a lot of energy. Okay, so that's what we know from the problem. We also know some facts about the Earth right here. We're solving for mass in kilograms. We're going to use this little formula. And what I did here is I broke it into 2 steps. We're going to solve for the numerator first, so 2 times the radius, which is the sum of the Earth's radius plus the altitude, times the energy, which is negative. So we end up with a negative value on top, this very large number, put it on top. And then we are going to take that and divide by the universal gravity constant and the mass of the Earth, and it's also negative. So we do that. So we have a negative divided by a negative value. We end up with about 6,000 kilograms, and that's how you do this problem. So try it like that. You could do it all at once. If you're not really good at using your calculator, I really recommend breaking things up and carefully documenting as you go. I try to account for rounding, so if you don't get exactly what I got, I set a little window, plus or minus, so it should be just fine. Good luck.